Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
Thank you, Fred, and thank you, everyone, for being here. It's a pleasure to give this lecture. And as Fred mentioned, I'm talking about exploring Mars with the Curiosity rover. So I'll start with why do we go to space? So this is my view. First is to study the evolution of the solar system, to study the origin of life, to study life in extreme conditions, and to protect the Earth from hazards, as you saw, a few months ago, I guess, right, in Russia. How did we get here? The solar system started from a plume of dust in space like this, collapsing. And what determined the main composition of the planets is the distance from the sun and the mass. And the solar system is about 4.5 billion years. The universe is about 15 billion years. And as soon as the solar system starts forming, the Earth starts cooling down. We have, in the oldest rocks that we find on Earth, evidence for bacterial life. So the question is, if there are other solar systems much older than ours, did life start there? If life started there, it could be much more evolved than here on Earth. So this is really exciting. So here's one of my favorite pictures from the Hubble Space Telescope. It's a real picture of a solar system just starting. So the plume of dust has already collapsed in a disk. There is enough mass in the center to collapse together that the sun already formed. And this will end up forming a solar system similar to the one that we have here. Now the question of life. Everywhere that we find water on Earth, we find life. Doesn't matter how extreme the condition is, like how saline the water is, how acid the water is, how cold it is. If there is liquid water, there is life on Earth. And one big surprise was in the 1970s, the Alvin, this submarine that can go really deep, in this case was the order of 4 kilometers below the surface. And the geologists were just studying the boundary of plate tectonics near the Galapagos Islands. And a big surprise was that this source of hot water in this boundary had a chain of life around them that was independent of solar radiation. And that was a huge surprise. And since then, we believe that life started in those hot vents. And since then, more than 500 species of life were found around those vents. And here's an example of one that's a vent that's full in iron. And all the life has the color of rusted metal there. Now another exciting thing is that, like on Mars, the theme of NASA for exploration of space is to follow the water. And the reason for that is that everywhere that we find liquid water on Earth, we find life. So if we want to find life elsewhere, we should follow the water and look for evidence of liquid water. Mars is very cold today, but there are some salts that can lower the freezing point enough that we could have liquid water on Mars. And so the question then, if the water is really saline, like you need in order for it to be liquid on Mars, do we have, can life evolve in those conditions? And here's an example from the Dead Sea, a bacteria that is happy in very saline water. So very saline water is okay for life. And here's one exciting, this was found, I think, 2 years ago. In Antarctica, there is a lake below this glacier, and in the summer, spring, through cracks in this glacier, some of this water spilled off, and this lake that has been protected from solar radiation for 1.5 million years. So it's very old water, not in contact with the sun, the solar radiation. And through these cracks, as the water starts coming out, this really saline water, it's rusted because it's rich in iron. And there is bacterial life that was found there. So another really example of extreme conditions that's like what you expect on Mars, even the same color as Mars. Mars is red for the same reason, it's rusted, and we find bacterial life there. So now going back to the solar system, what are the best candidates for life in the solar system? First, Europa, a moon of Jupiter. It's covered by ice, but because of the tidal between Europa and Jupiter and the other moons around, it's being warmed, and there is evidence for it's completely covered by an ocean of liquid water, and it's probably a saline water. And so that's a really good candidate for life, but it's a difficult place to reach. We have to go through a deep layer of ice to be able to reach this liquid water there, and it's far from Earth. There's Mars, where there is evidence of perhaps liquid water activity in the past. And Mars is relatively close to the Earth. Every 2 years, we can send a spacecraft there who arrive within 8 to 9 months. So it's a relatively easy place to get to. And then Titan, a moon of Saturn, that's really cold. The temperature at the surface of the order of 90 degrees Kelvin. And there is evidence of seas of ethane and methane, so hydrocarbons. And here is evidence of that. So those are the 3 best candidates for life in the solar system. But Mars is the one that's the easiest to get to, and that's the reason for this big focus on the exploration of Mars. Now to give you an idea of the size of Mars, Mars is smaller than the Earth. So the gravity acceleration is about 1/3 of the one on Earth. Has a very thin atmosphere. The density of the air at the surface of Mars is about 1% of the density of the air at the surface of the Earth. So it has an atmosphere that as a spacecraft is reaching Mars, it's going to heat up as it goes through the atmosphere in very high velocities. But the atmosphere is not dense enough to break the spacecraft. So the landing on Mars is very difficult. So why follow the water? I just discussed this is because everywhere that we find water on Mars, on Earth, we find life. Extreme acid environments, extreme saline, deep caves. Bacterial life was discovered more than 3 kilometers below the surface in a cave in South Africa. And million years old brines like that lake below a glacier in Antarctica. So here's just the focus on Mars. Then NASA and the European space agents try regularly to send a spacecraft to Mars. Now we have the Mars Science Lab, or Curiosity rover, at the surface of Mars. One of the rovers that was launched in 2003 is still alive there. And there are a few satellites, I believe 2 or 3 around Mars now. So the more we look at Mars, the wetter it's get. So this is a cartoon that I got from the web. And this is really exciting. So it's making more likely that one day we'll find evidence for bacterial life on Mars. So what's the Curiosity rover? It's basically to simulate what a geologist would see at the surface of Mars. We have a stereo camera where the distance between cameras is more or less like the distance between your eyes. It's about 2 meters above the surface. In this case, the rover is nuclear powered. And to be able to survive with a high probability for about 2 years on Mars. And has a robot arm with a bunch of instruments here that I'm going to talk a little bit about. And the goal was to land in a place that would be relatively safe to land, and to be able to rover to a place that scientifically is really interesting. So that's what drives this 2 years of mission time. So the science goals of the mission is to assess the biological potential of a site. That means to go there and to see if life, bacterial life like we know on Earth, would be able to survive in this place. So if that's the case, then we can claim that Mars is habitable for the bacteria that we know here on Earth. And to look at the geology and geochemistry of this place, and to look at the role of water not only in the evolution of the planet, but in the site there. So we land in a place where there is evidence of water activity in the past. And another goal is to find out what's the radiation dose that a human mission would be subject to, not only in the trip to Mars, but also at the surface of Mars. And we refer to that as preparation for human exploration. So my personal goal is to study the possibility of wet brines, this really salty water there at the surface of Mars. And some of those salts, they can absorb a really small amount of water from the atmosphere and melt into a liquid that could be habitable. And search for habitable zones, that means search for those wet material just below a thin layer of soil. And another theme is to look for, the main active geological process on Mars today is sand and dust moving around. Every few years, there's a dust storm on Mars that completely covers the planet. In fact, the first US mission to Mars arrived there during one of those dust storms. So all the planetary scientists in the mission were really excited. And as the spacecraft arrived on Mars, we couldn't see anything. Mars was completely covered by dust. Only after a few weeks, the highest peak started appearing at the top of the dust layer. So those dust storms are common on Mars. So a little bit about the mission. It was launched in Thanksgiving 2011. There's a picture of the launch. The trip to Mars took about 8.5 months to arrive on August 6, 2012. And there is this very unusual landing system. And the reason for that is that this rover is much bigger, much heavier than any other one sent to Mars before. It weighs about a ton. It's about the size of a Mini Cooper. So it's really big. It was difficult to land. If you try to land with an airbag like the 2003 mission and the Pathfinder mission in 1997, the airbag would rupture in the impact on the surface. And if you try to land with the rover on top of a platform, the platform goes with rocket engine all the way to the surface, then lots of sand and dust would be ejected and could damage the rover. And another problem would be the platform would be very high, would be very difficult to maneuver the rover from the top of the platform to the surface. So if you look in detail, that was the conclusion of the JPL engineers, you conclude that this is probably the safest way to land on Mars. But the problem is that this new system was never tested before. The first full test of the system was landing on Mars. So that's why people got so excited when it landed safe. It was the first full test. And it's like a sky crane helicopter powered by rocket engine that comes down to about 10 meters above the surface. Then the rover is lowered at 3 cables. When the rover touched the surface, that the tension in the cable reduces, the cables are cut, the upper stage flies away, and the rover stays right at the surface. Everything happens correctly. And there are 72 critical events. If one of them failed, that would be the end of the mission during the landing. So it's a very, very difficult thing to do. And as I mentioned before, the mission is about 2 years long, and the reason for the 2 years is that we want to land in a safe place and be able to rover to a scientifically interesting place, and that requires about 2 years. And the science payload is about 84 kilograms, so 1,000 kilograms of total mass, 84 in science instruments. So this is a picture of the rocket the night before launch. This launch and going to Mars. Some of those launches are during the night, like the 2008 Phoenix mission was during the night, and the launch at night are cool because you can see the planet and you can see the rocket is in the right direction. In this case, you cannot. So the landing on Mars. So I have 2 short movies of the landing, and you're going to see how exciting it is. And I want you to pay attention. One of them that's real images that were taken during the landing. About 1,000 images were taken as the MSL reached the top of the atmosphere of Mars, going away all the way to the surface. And there's a little animation of those images with real voice in the background of people during the landing. And what you're going to notice there is that you see the last few images, the rover is already at the surface, and no one is cheering yet, because the sky crane, the tension in the cable was reduced, the 3 cables had to be cutted, and people start cheering only when we knew that the sky crane was accelerating at high speed, away from the rover, and the rover was not moving, because if one of the cables were not cut, it would be the end of the mission. That was a nightmare. Okay, so the landing. Oh, this was the most precise landing made on another planet so far. And the landing system, there are thrusters here that are controlling the angle of attack, like if you're landing an airplane. So the parachute opens. So it started everything at 12,000 miles per hour. Then just the friction with the atmosphere reduced the speed by a factor of 10. The parachute another factor of 10. So you're still at 200 miles per hour. And then the sky crane is for the last deceleration step. So now the rocket engine, the plumes start interacting with the surface, and it's going to lift lots of dust. That's much worse. Okay, I'll skip this. And this, to communicate with the Earth, it's not very easy. And what NASA requires now so that we understand if anything goes wrong during the landing, what happened. So you have to communicate through the whole time with the Earth. And the way that we did in this case was one of those satellites around Mars moving over the landing site at the time that MSL was landing. And so the MSL is sending the radio signal to the satellite sending it back to Earth. This satellite had a high-resolution camera, so one of the engineers at JPL had the idea of pointing the camera towards where we were going to be landed and take some pictures. And this is a real picture of the MSL falling on the parachute. So it's the second time that we have a picture like that. Phoenix in 2008, we have a similar picture. So one of the things that we did here at UFM, some of my students, was to look at this interaction of the rocket plume with the surface. And we conclude that during the landing, this is a real lab simulation of that interaction, that the topsoil would be excavated, all the sand would be removed, and would be blown towards the rover. So that requires some adjustment in the landing system to avoid that the rover would be blasted with sand. And here's during the descent, there was a camera here. Oh no, the camera was under the rover, looking down, and here's one of the pictures of when the rocket engine started interacting with the surface. So this is a real picture of sand and dust being ejected as the rover approached the surface. And here's that little simulation that I mentioned with real pictures taken during the landing. So pay attention to what people say in the background.
altitude on chute. We are decelerating.
So here's the aeroshell being released.
Decelerating and descending. We are at 150
So those are
meters
some
per second.
sand dunes that we landed close by.
Dynamics phase. Come back again with wrist mode dynamics.
Wrist mode is nominal.
We are 9 kilometers and
8
descending.
leads active. Valid range.
Net filter converged with a velocity correction of 0.7 meters a second.
We've acquired the ground with the radar.
An altitude of 8 kilometers.
Seat chill has separated. We've found the ground.
Expand tones due to earth occultation as expected. We're
Standing by to
all the way
prime
in.
the MLE engines in preparation for powered flight. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending.
Flight EDL, we got some Tweedo warnings. It is in battle short mode, so I should power through them.
Direct Earth communications at this time. We may have lost it already. We're down to 86 meters per second at an altitude of 4 kilometers and descending. We've lost tones from Earth at this time. This is expected. We're continuing on Odyssey telemetry.
Ground solution equals minus 10.8 meters, vertical velocity of minus
We are priming
82.8
tower
meters per
descent latch
second.
start enabled, standing by for backshell separation.
Signal to Odyssey is still strong.
We are in powered flight.
So the sky crane is on, the rocket engine.
We're at an altitude of 1 kilometer and descending, about 70 meters per second.
Signal to Odyssey remains
Down to 50 meters per second. 500 meters in altitude.
So now there is a radar that's looking for a very flat place to
Standing by for
land.
sky crane.
Constant velocity accordion nominal. Altitude error 5.9 meters.
We found a nice flat place.
So
We're
you see the
coming in ready for
interaction
sky
with the
crane.
surface?
Down to 10 meters per second. 40 meters altitude.
Now the rover is inside a big
Sky
dust
crane
of
has started.
plume.
Descending at about 0.75 meters per second as expected. Expecting bridle cut shortly.
Signal to Odyssey remains strong.
Tango Delta nominal.
So it's landed, but no one's steering yet.
Yeah. UDLCOM configured.
Review stable.
UHF telemetry.
You can see the picture is still at the surface.
UHF is good.
Touchdown confirmed. We're safe on Mars.
Okay. And for me, one exciting picture was this, because we predict that the top soil would be completely removed, a rocket below would be exposed, and this is where one of those rocket engines interact with the surface. And here is a picture of the deck of the rover after landing. You can see all those pebbles there. So it was lots of sand and dust being ejected around. And here is the cover of one of the cameras, completely covered by sand. Here is, we got a call after we landed. I think he didn't believe that we were going to land safely either. So here's what the president said. But now a little bit about the instrument. There is a very complex sampling system. This is at the tip of the robot arm. There is a bunch of drills and a system here that collect the samples of soil and rocks and deliver to two instruments that I'm going to talk a little bit about then. And okay, I'll just say this here. Here it is. We have the cameras, stereo cameras. We have a laser at the top of the mast that you can shoot at rocks that between 3 meters and 10 meters away from the rover, and then you pulverize a small fraction of those rocks, and based on the brightness, you know what the composition is. And what this instrument has been finding is that almost every time that we shoot the laser beam, the top material has a very high hydrogen content, and that in the rocks usually decrease with depth. Just means that the top dust is reaching probably water. And as you go deeper, there is less, except some place that we found more hydrogen at larger depth. That's very exciting. There's an instrument here that measures, it's like a weather station on Mars, measure temperature, pressure, wind, water vapor content, and ultraviolet flux of radiation. There is the red here that measures cosmic radiation. There is the DAN that measures the hydrogen content at the surface down to about a meter deep. And most of the hydrogen there, we believe it's water. So it's basically looking for water below the surface. And SAN is the sample analysis at Mars. We collect samples of soil or rock, and then we heat them up in a little oven, and we look at the volatiles coming out as a function of temperature. So this instrument has been detecting the water absorbed in the soil. This instrument discovered some salts that can produce liquid water on Mars today. CanMin that measure the mineralogical composition of the soil and rocks. MARDI is the camera that took those images during the descent. It's almost like a microscope, a high resolution camera at the tip of the rod arm. And there's another instrument here to measure the chemical composition of the rocks and the soil. And those are the instruments. Now I'll talk a little bit about the possible landing sites that we are considering and why the one that we landed is the one that was selected. So Phoenix in 2008 landed over there in the polar region of Mars. And the reason that we went there is because data from an orbiter suggests high hydrogen content in the top soil, so much that more than 50% biomass of the soil would be ice if that hydrogen was from H2O. And so the goal was to land there to find out if it was really lots of water ice very close to the surface, and we discovered that water ice. And then the Vikings, Viking 1 and 2, landed in those two sites here. The Mars Pathfinder in 97 landed here, and the Opportunity and Spirit in 2003 landed here. So for MSL, we were considering the white points here, and Gale Crater here is the one that was selected. And one of the constraints was that could not be too far from the equator because of the rover design. And we want a place where there was evidence of water. So Gale Crater, where we landed, is right there. And MSL came from the bottom left towards the crater, so flying here. And you can see that in the center of the crater, there is a very high mountain. And MSL landed between that mountain and the ring of the crater. So it's amazing that from Earth, we can launch a spacecraft and land in this place. And the reason for that is that geologically is a very interesting place. But there is a problem. Landing there, it's not easy, especially if a system that the first full test is the landing on Mars, right? Here is where MSL landed, right here. So here is the mound at the center of the crater. The dark material around it is a basaltic sand dune. And here is what we call the landing ellipses. It's basically the error in the landing, the uncertainty in the landing. Started from the Viking 976. We could not land it in this crater because the uncertainty in the landing would make it very unsafe to land there. Then we go down to the one before MSL, the Spirit and Opportunity. We also would not be able to land it there because the landing ellipse is much larger than the safe area to land. So MSL has a very small landing ellipses. One reason for that is that the entrance on Mars is controlled. There are those thrusters that controlling the angle of attack, like you control airplane during a landing. So it was the most precise landing ever made in another planet. So the goal then and why we went here, this is the crater. The uncertainty in the landing was only the error in the landing a few kilometers. And the goal was to land here and rover all the way to this area where there is really strong evidence of water activity in the past. So that's right there. So we would be roving, crossing those dunes and go there. But I'm going to show that after we landed and we start looking around, we decide to go first in the opposite direction. And that turned out to be a very good decision. So we landed there in the top right, and we rover to the green dot in the left. And why? Because the terrain there was very different. Where we landed was very sandy soil. In that region, from satellite images, we could see that the ground was very fractured. So we went there to check what was causing those fractures at the ground. And the goal is to go down in the lower reaches of Point Sharp in the bottom of the picture here, where there is evidence of liquid water activity in the past. So this is the first 100 days at the surface of Mars. So the place where we landed is darker because of all the fine dust was removed during the landing by the rocket engines interacting with the surface. If you remove the very fine dust, the surface becomes darker because the fine dust scatters more solar radiation. And here is 21 days, 24, 26, 29 after landing. We call a day on Mars a solar day, because a day on Mars is 24 hours and 40 minutes, a little longer than on Earth. And I forgot to mention in the right there, you can see that area is very different. It's lighter in color, and the terrain is more fractured, and that's why we went there. And here is a picture that, if you look carefully, you can see the track of the rover at the surface. On the right and the left there is the dark region where the dust was removed during the landing. And then you can see the track of the rover. And you can see the bright spot here, that's the rover there. And you can see that the terrain here is very different than the one where we landed. Okay? And here is one of the first images that got people in the mission very excited. Doesn't seem that exciting, but all those white spots. So we see everything on Mars is reddish. And then suddenly we see something completely white. And then we start seeing more and more and more. And then for a while, people were very scared because they thought all those white things there were maybe pieces of the rover or things that we could not understand. And then we discovered that they are gypsum. And this is really exciting because gypsum forms with water. So probably water at 30, 40 degrees Celsius, that's optimum for gypsum. So this is evidence of liquid water in the past in this area. And then there's another rock. This was even more exciting. Well, we start finding rocks that looks like dry mud with all the cracks filled with gypsum. So that's really suggests strong water activity in the past. And probably the hypothesis that mostly widely accepted now is that there was some volcanic activity there. Subsurface ice melted and percolated through the rocks, and that's how those gypsums were formed. And that's where the terrain is dry and looks like dry mud and very fractured where we are. And I'll talk a little bit about that later. So now going back to 2008, the Phoenix mission to Mars. That's when we found the first evidence of water, the first time that we really touched water ice on another planet. So Phoenix landed, let's go back, with rocket engines going all the way to the surface. And it was much smaller than MSL. I forgot exactly weight, but I think it was about 300 kilograms. So there are 12 rocket engines that assisted the landing. And Phoenix didn't move, so the goal was to land and dig, had just a robot arm to dig. And we studied here at the University of Michigan also the interaction of the rocket engines with the surface to see what could we learn from that interaction. And our initial idea was just more to learn the properties of the soil. But then we realized that if there was water ice less than a meter deep, more than 50% by mass, that's what the satellite measurement suggests, then that interaction would completely remove the topsoil and expose the water ice below the surface. And then, as soon as we landed, we start requesting pictures with the camera in the right arm from under the lander. And for us, this was one of the most exciting pictures showing the ice exposed there. And, but another interesting thing was that in one of the struts of the lander, we saw all this junk there that we could not really understand what it was. So one of my focus in this mission then was to try to understand what was going on in that strut. And the initial hypothesis was the interaction of the rocket plume with the ice, partially melt the ice, and just spill the stuff around like dry mud. But what was puzzling was that some of the, we call spheroids forming there, was like really spherical droplets that were changing with time. So that's what I show next. Oh no, first I show digging the first trench on Mars. Is a sequence, and I'll go back. This was very, very exciting because first we see that that ice exposed, and then we dig the first trench. We were expecting to see ice about 10 to 20 centimeters below the surface, and because it's so cold on Mars, especially in the polar region, that ice was supposed to be harder than concrete. And now if you look at the sequence here, look at what happens. We're digging, digging, digging. This is a few centimeters below the surface. A chunk of ice was removed, and it was like scooping soft ice cream, completely different from what we expected. So in my mind, this was the first evidence of a brine, really saline, partially frozen mixture on Mars. And this would be exciting because, as I showed discussed before, on Earth, in those saline water, you find bacterial life. And here's another picture of that. That layer of this thin, soft ice was a few millimeters thick, was only, I forgot exactly how much, but less than 5 centimeters from the surface. And pure water ice would sublimate that deep. Would not be stable, but a very saline mixture is stable. You can see that there is a very sharp front, so it's evidence that this was liquid flowing around. And then if we go back to another trench that we dug, this is more than 10 centimeters deep, and the ice here is as hard as concrete. So that's what we expect, not the previous one. And now we look at the strut of the lander. You can see 2 spheroids here. There is a range of brightness that suggests going from frozen to melted. As you melt the ice, it becomes darker, right? The liquid water scatters less light than the ice. That's what we see here. And we see another one that's really dark, so it's probably completely liquid. Okay, now you can see that they are moving. And what's really exciting, if you see this one that grows really large, this was more than 1 centimeter in diameter. And if you do a calculation, up to 1 centimeter of diameter, a spheroid would be stable on Mars. And as it grows, it would fall, drip. And as this one grows, becomes darker, it disappeared. So probably drip. And what's more important, if you have a salt that's absorbing water from the air, as the spheroid created by that absorption of water from the air grows, it grows in proportional to the initial amount of ice. So the volume is always proportional to the initial volume. And that's what we see in all those here. The other thing is then if you remove the salt, for example, by causing something to drip, nothing else should grow there. That's exactly what we observe here. So we keep looking at this for a few hundred days on Mars. And then at the end of the mission, some people were arguing that this was ice. if there were ice, as it gets colder, as we are approaching the fall, winter, then you would expect to see more and more ice. And if it was a brine, as it freezes, it would start sublimating. So you expect to see less. And that's exactly what we see here. So it's inconsistent with what the ice is consistent with brine. So now moving back to MSL. So we landed, and then we start roving around. So this was the first image after we landed. After all that excitement that you heard. This is one of the navigation cameras looking towards the center of the crater. That's the mountain that we landed nearby. And I think it's unbelievable that you can land in a place like that. And here's one of the first panoramic images of the site. So you can see very sandy, and then that really dark dune that some people in the mission is very excited about it because they think this is a really good place to search for bacterial life. And some of the rocks nearby where we landed. So this is the first area that we dug. And some of us got really excited about this too, that you can see this gradient of color with depth. So maybe suggesting some interesting activity here. If you have a source of water below the surface, you would expect to see those gradients. But what's interesting here is the color. It's sort of rusted iron at the surface, and as we dig, everything has the same color. So that's the color that we're used to Mars. And that those rocks around, and this is probably what people refer to as a volcanic bomb. It's basically a chunk of lava ejected by a volcano that goes spinning around, stretches, and that's how those cracks form. So it's volcanic and sand material. Not too exciting if you're looking for bacterial life. And this is a close-up of the soil. Each grain here has about 3 millimeters in diameter, and everything is covered by this very fine dust. That's what's falling from the air on Mars. The atmosphere of Mars is really dusty most of the time. So this was one of the first place where people start getting excited about water activity. Now this looks like more a sidewalk, right? Concrete. So we see all those round particles here that could be abraded during water activity, and that the material is really solidified like you expect in a sedimentary material. But still not really approved. And then going back to this, the place where we later found those rocks that the cracks are filled with gypsum. So that's the first really clear evidence of liquid water activity, but probably together with some volcanic activity in the past. And here's where we are now. You can see the terrain is full of cracks. This image doesn't show, but there are voids on the ground that you see. People have been referred to it as gopher roads, look like a snake hole on the ground. So I think that's evidence that the soil is very, porous in this region. And that's what you expect if there was a big source of ice and there was some volcanic activity. Some of that ice was melted and there was lots of void on the ground. And maybe there is still water sublimating around, interacting with the lower surface and the atmosphere. And here's the first rock that we drilled. So before drilling, we cleaned the rock. And this was really exciting because remember, everything that we have seen on Mars so far has this color of rust. And then suddenly we clean something that has a completely different color. So maybe something really interesting is going on in this place. And looking at more detail, and the rock there are lots of cracks, and it looks fragile, and you can see material embedded in the rock. So now we conclude those are really sedimentary rocks. And now, a closer view of some of those. And this is the first drill made in another planet. So it took a few weeks for us to drill this first hole. because it's a very complex process to do this remotely, especially because you don't want to damage the rover. There is no way to fix it. If you damage, that's the end of the search for evidence for bacterial life, for example, in those sedimentary rocks. And what we can see here is that as we drill the rock, the color is completely different from the rusted material around. And that's really important for life, this gradient. Some places were oxidized and others not. So that's why I think NASA had the press release a few days ago stating that the place that we are now on Mars is habitable. So there is condition for bacterial life there probably in the past. And what's very interesting, as you can see, as we are pressing the rock here to drill, things move around, and those cracks, the materials are porous. Now, just to contrast, this is the place where we landed. You know, that area was very sand soil, and doesn't matter how deep we dug, the color was the same, this rusted iron. The place that we landed, that we are now, is completely different. Looks like dry mud, and here is a place that was damaged by the rover moving around, and you can see everything that's damaged has either that color more like concrete, and lots of the cracks are filled by very white material that's gypsum. I cannot show, there is a rule in the mission, you know, everything that we discuss in public has to be publicly released by NASA, and only next week there will be a conference, will be the first one that lots of people from the mission will be going and giving lectures about some of the discoveries. So one of the things that some of my colleagues are going to talk about is evidence that we found that this place here is a net source of water. There is water, probably ice or some of those brines below the surface that's producing, releasing more water there than it's absorbed during the night when it's cooler. So this is a really, really interesting place. And there is a few reasons for making that statement. One of them is that as the rover is moving around, we're measuring the temperature of the ground and the temperature of the air. And as we move from that sandy region to this looks like dry mud, the thermal inertia changed. That means where we landed, the minimum temperature at night was minus 90 degrees Celsius, and the maximum during the day was 10 degrees Celsius. And suddenly, when we got in this region, that changed to the minimum being minus 80 and the maximum 0 degrees Celsius. So you go from very large fluctuation to a much smaller. But what's more interesting, the difference between the temperature of the air and the ground, the maximum decreased from 15 to 5 degrees Celsius. And that's an indication that besides heat flowing from the ground into the air, there's something else that could be water evaporating and cooling down the surface, but very small amounts. So the science results, so this is the 8th month of a 2 years long mission. So we are just really starting doing the science. A big part of the first few weeks or even months is just testing the instruments. That was the first drill, so we were just learning how to drill on Mars. And the initial results are still being discussed and checked. In the way that we do that, the first 3 months of the mission, all scientists tried to spend as much time as we could at JPL, working together and getting to know each other. And now we are operating remotely. So people went back to their place, like I'm here in Michigan, there's people in Europe, all over the United States. And we do everything through the internet and telecoms. So we have, after each day, a group of people is responsible for the operations. And then we discuss the science results. And we have a few days per week science discussions where if you come up with any idea, doesn't matter how crazy it is, you present it, it's discussed, and then if most people agree, you can go forward and make your ideas public. But we try to avoid that crazy ideas don't become public without any venting inside. So the first results will be coming next week. So if you're interested, pay attention to the Lunar and Planetary Science Conference next week. That will be, probably will be lots of press about the most exciting results. And here is just show there's lots of participation from U of M in those missions. And here is just a U of M group that's part of this mission at JPL. And me and some of my students here are participating in the science group. Those who are most engineers. And those missions has a few hundred engineers working on them. And we work for more than 10 years. That's why people get so excited when land on Mars. So you invest 10 years of your career on it, and it could be the end during a bad landing. And there is, in this mission, I think, or the way that we become part of the mission is you propose science instruments, forming teams all over the world, and then if your instrument is selected, you become part of the science team. And MSL initially had about 100 scientists, and then we can invite, like I can invite my grad students or students to be part, and then you propose that to the mission, and then they become part of the science team also. And now I think it's about 300 people. And we all have those discussions, as I mentioned, through phone and internet, and works amazingly well. It's just unbelievable how polished the process is. So that's it.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.